Hello everyone. In this part of our robotics lab, I would like to share with you what we have learned and accomplished. We are going to have 4 topics: TinyML, edge device, prompt engineering, and computer vision. For TinyML or tiny machine learning, is a fascinating area of AI that brings intelligent decision making to small, low-power devices such as microcontrollers. In our lab, we use the Arduino Nano 33 BLE Sense, a compact board packed with sensors and capable of running simple machine learning models directly on device. TinyML is the process of running machine learning models on devices with very limited resource, usually less than 1 megabyte of memory and very low power consumption. The main benefit of TinyML is that it enables real-time AI processing at the edge without needing to send data to the cloud. This means faster response, more privacy, and even longer battery life for portable devices. Real-world examples include smartwatches, environmental sensors, smart home devices, and health monitors that can process data instantly and make decisions without relying on constant internet connection. In our lab, we carried out a series of experiments using the Arduino Nano 33 BLE Sense programmed to Edge Impulse. First, we flashed the board with Edge Impulse firmware. This allowed us to connect the board to the Edge Impulse Studio and upload live sensor data. We divided our experiment into 4 main groups, each exploring a different sensors and machine learning use case. The first group focused on the microphone. Using audio data collected from the board, we trained a model to recognize 3 different parts: the sound of saying the letter A, the sound of B, and silence. We visualized the sound through pulse density modulation, then converted that into spectrograms for the machine learning models. After deploying the model back onto the board, we could speak into the microphone and see live predictions whether the board heard A, B, or nothing. This is similar to the way smart assistants detect wake word. The second group used the gesture and proximity sensors. They trained the device to respond to different hand gestures, with the Arduino board displaying different LEDs colors depending on the gesture detected. This demonstrated how TinyML can be used for contactless interaction, useful for public kiosks or hygiene-sensitive environment. The third group explored the use of the accelerometers. The Arduino was programmed to classify its own orientation, such as lying flat or standing, and change LED colors accordingly. This kind of sensor-based recognition is similar to how fitness trackers or machine monitoring systems work, detecting motions, patterns, and physical activities. The final groups implemented person detecting. Using a pre-trained model from Edge Impulse, the model was able to classify images from the board's camera such as person or not persons. This shows how vision-based AI can even be run on low-power devices, enabling use cases in security, automation, and occupancy monitoring. So where is TinyML used in real life? In healthcare, for monitoring heart rate or detecting faults in elderly patients; in agriculture, for soil condition monitoring or pest detection with smart sensors; in smart cities, where noise, air quality, or traffic can be analyzed instantly using Edge AI. The main takeaway is that TinyML make it possible to deploy intelligence anywhere, even in remote or battery-powered environment where regular AI wouldn't be feasible. To wrap up, our TinyML project gave us a hands-on understanding of how AI models can run on tiny devices using real-world sensors and efficient code. We learned how to collect data, train models, and deploy them back onto the board to perform tasks like sound detection, gesture control, and object recognition. Now let's proceed to the role of edge devices in AI and robotics. With a focus on deploying computer vision model directly onto hardware like the Jetson Nano, our goal was to understand how data can be processed locally right at the source without relying on the cloud. An edge device is a physical piece of hardware that processes data close to where it is generated, at the edge of the network. Instead of sending data to a remote server, edge devices allow us to make decisions locally and instantly. This improves speed because there's no delay from internet communication, privacy because sensitive data stays on the device, and reliabilities, especially in areas with limited internet access. Examples of edge devices include smart cameras, IoT sensors, wearables, and the Jetson Nano, which we use in our lab. In the lab, we work with the Jetson Nano, a powerful AI computing platform developed by NVIDIA. Our goal was to use it to run real-time object detection with a model called YOLO V11. Here's what we did step by step. First, we flashed the Jetson Nano SD card with a custom Linux image using Balena Azure. We connect the board to power, display, and Wi-Fi. Next, we install the necessary Python libraries and clone the YOLO V11 repository. We then train a custom object detection model using RoboFlow using two classes, phone and wallet. After training the model using Google Colab or an A100 server, we downloaded the best point PT file and deployed it to the Jetson Nano. Once set up, the Jetson Nano could detect these objects in real time using a webcam. To make it even more practical, we integrated Line Notify by using a personal token. We wrote a Python script to send alert to a Line group or account when a specific object like a phone was detected. This shows a powerful real-world use case. Imagine a smart camera in a classroom that sends a message. If a student is using a phone or a home surveillance system that notifies you if a person is detected while you are away. Edge devices are used in many industries, in manufacturing to monitor equipment and detect defects, in retail for automated checkouts and customer flow tagging, in securities to recognize faces or detect intruders, in healthcare for monitoring patients in real time. The Jetson Nano is a perfect example of a low-cost, high-performance edge AI platform that can make this application accessible even for small projects or prototypes. So why are edge devices so important? Because they allow us to bring intelligence to the real world without needing expensive servers or constant internet access. They are the foundation for smart cities, autonomous vehicles, and next-generation robotics. Our lab experience showed us how to collect data, train AI models, and deploy them directly to an edge device. This process is the backbone of many smart systems today. In summary, working with the Jetson Nano taught us how AI can be brought directly to the hardware level. We built an intelligent system that could see, recognize, and react in real time. This project not only deepened our understanding of computer vision and edge AI, but also demonstrated how compact devices can power real-world applications. Now let's proceed to the prompt engineering for generative AI. As large language models like ChatGPT, DALL-E, and Claude become more integrated into our daily life, knowing how to communicate with them effectively is becoming a valuable skill. This is where prompt engineering comes in. Prompt engineering is the process of crafting precise input instructions called prompts to guide an AI to produce a desired output. Think of it as giving instruction to a really smart assistant. The way you ask a question, the level of detail you provide, and the structure of your prompt can all affect how well the AI responds. We learned that prompting is not just trial and error, it's a technique. And with the right approach, we can make AI more accurate, creative, or even more human-like in its response. Throughout our lab, we explored multiple prompting techniques, each designed for a different type of task. Here's a summary of what we practiced. Chain of thought prompting. This technique helps the AI reason step by step. Instead of asking for a final answer right away, we prompt the AI to expand its reasoning process, similar to how a student would solve a math problem. Interview pattern promptings. Here we simulate an interview-style conversation. This allows us to extract information in layers, just like asking follow-up questions to an expert. Tree of thought prompting. This approach allows the AI to generate multiple paths or solutions, then evaluate each one. It's similar to brainstorming with branches. Text-to-text promptings. We also learn how to transform text, such as summarizing, rewriting in a different tone, or converting casual speech into a formal writing. Text-to-image prompting. Finally, we explored image generation using tools like ChatGPT. By describing a scene or object in details, we can generate realistic or artistic images. We practice controlling style, lighting, and resolution, and composition, all using just words. Prompt engineering is already being used in customer support through chatbots that understand user intent better, marketing for generating product description and social media content, software development where tools like GitHub Copilot write or complete code from natural language prompts. As AI becomes a core part of many industries, the ability to prompt effectively becomes a crucial digital skill. This skill is valuable not only in technical roles but also in marketing, education, content creation, and more. As generative AI becomes more accessible, those who can engineer prompts effectively will be the ones who get the most out of it. Now let's proceed to the final topics, the computer vision. This area of artificial intelligence focuses on teaching machines to see and understand image or videos, much like how humans use their eyes and brain to recognize objects, shapes, and patterns. Computer visions involve techniques that allow machines to process and interpret visual data. It's a key component in many modern technologies, including facial recognition system, self-driving cars, medical image diagnostics, and even things like barcode scanner or document readers. By using computer visions, machines can make decisions based on what they see, helping us automate tasks that previously required human observation. In the lab, we use Visual Studio with C# and the mGuCV library, which is a C# wrapper for the popular OpenCV framework. Our goal was to work with live camera feeds, manipulate images, and build basic image processing applications. Here's what we did across 3 main assignments. The first assignment, which is the webcam setup and live feed. In the first assignment, we learned how to connect a webcam, capture a live video feed, and display it inside a window form application. We create a simple UI with start and stop buttons using video capture, and this gave us the foundation for building computer vision application using real-time video input. For the second assignment, camera control and histogram displays. In the second task, we add more functionalities to our applications. We build a histogram display to show the distribution of brightness in the image and allow the user to capture and save images from the live feed. This assignment shows us how to analyze image in more detail, which is essential for industrial or security camera systems. For the third assignment, image thresholding and processing. In the final assignment, we load an external image like a coin and applied image thresholding. This technique turns an image into a black and white based on brightness values, which help in separating objects from the background. This process is widely used in real-world applications like object detections, OCR, shape and pattern recognition. We also practice adjusting threshold levels manually to see how it affects the qualities of object edges. What we learned in the lab has direct applications in many industries. In manufacturing, computer vision systems detect product defects using cameras and thresholding techniques. In medicine, doctors use vision-based AI to analyze scans and detect diseases early. In security, facial recognition and motion detection systems rely on live video feeds. Our experiments simulated the core of this system, showing how simple components can be scaled up for real-world solutions. To wrap up, this lab gave us practical experience with real-time image processing using webcams and C#. We learned how to capture video, analyze brightness with histograms, adjust camera settings, and process images using thresholding. Camera vision continues to grow in importance, powering innovations across robotics, healthcare, automations, and smart cities. Thanks to this lab, we now have the tools to start building intelligent systems that can see and understand the world around them. Thank you for watching.